Okay, so this is Physics Section 3.2, Part 3. We are going to be looking at radioactive decay and different types of radiation. So radioactive decay, unlike all previously discovered chemical reactions, radioactivity sometimes results in the formation of completely new atoms. So if you remember back in chemistry, in a chemical reaction that, say, involves something like oxygen, the number of oxygen atoms we start with as the reactants, we will also finish with as the products. And this is the law of conservation of mass. In radioactivity, this isn't necessarily the case. So let's kind of get into why that is. Radioactivity results from having an unstable nucleus. So remember that the nucleus is made up of protons and neutrons. So essentially there's a proportion of neutrons to protons, if we think of like a ratio, that's not ideal for that particular atom, therefore it's unstable. It takes a lot of energy to hold those unstable nuclei together, so therefore when these nuclei lose energy and break apart, decay occurs. Radioactive decay releases energy from the nucleus as radiation. Radioactive atoms release energy until they become stable, often as different atoms. Often it doesn't become stable until that new atom is formed, so it's going to keep decaying until it finally reaches a stable final form. So the bottom here provides you with a decay series, and we're going to get into this in the next slide, but essentially uranium-238, so that's its mass, decays in several stages until it finally becomes lead-206. So it becomes a completely different element. An element may only have certain isotopes that are radioactive. So not all isotopes are radioactive. We talked about potassium-40 being radioactive and unstable, but potassium-39, that makes up the majority of potassium isotopes, is not dangerous to be around. So these isotopes that are radioactive are called radioisotopes. So potassium-40 is a radioisotope, where potassium-39 is a stable isotope. So the image in the bottom right corner is showing a decay series for uranium-238. We saw this on the last slide as well. Uranium is what is used in nuclear power plants and nuclear bombs. So looking at its decay series, it starts as uranium-238 and undergoes what is called alpha decay, which we'll look at in a few minutes, until it forms thorium. It then undergoes a two-step beta decay until it's back to uranium, and that's where we are right here. But because it's uranium-234 instead of being uranium-238. So this is still unstable, so it undergoes 5 stages of alpha decay, so 1, 2, 3, 4, 5, to form lead-214. So that's right here. It then undergoes 2 more beta decays and 1 more alpha decay, getting us to lead-206, which is the stable isotope. So right there. So there's a whole lot of decay until it becomes stable, and it releases energy at each stage along the way, which is why uranium is used for nuclear power. So a ton of radioactive decay releases a ton of energy. So we have 3 types of radiation, 2 of which were covered in the previous slide on our decay series. So these were discovered by Rutherford, who was the same guy who discovered the nucleus. Rutherford identified 3 types of radiation using an electric field. So to create this field, he used a radioactive source and a lead block to prevent the radiation from going off in undesirable directions. There's a hole that is streamlined the direction of the radiation, and once it was passed through the hole, there were negative and positively charged plates on either side. and a zinc sulfide coated screen, which would allow you to see. So sort of like a photographic plate does, it is affected by the radiation that hits it. So this allows you to see exactly where the radiation was hitting. So that's what that bottom image there is showing. So the radioactive source is streamlined into an area with these positive and negative plates. The positive alpha particles were attracted to the negative plates, because remember, opposites are attracting. Negative beta particles were attracted to the positive plate, so they bent up because they were attracted to the oppositely charged positive plate. And then our neutral gamma rays did not move towards any plate. So this wasn't attracted to either, so it would just travel in a straight line, hitting kind of the center of the plate. So these are our three types of particles, so alpha, beta, and gamma particles. So we're going to talk about these individually. So first type of particle is alpha radiation. Alpha radiation is a stream of alpha particles. They are positively charged and are the most massive of the radiation types. So this just means they have the most mass. Alpha particles are essentially the same as helium atoms. Alpha particles are represented by the following symbols. We represent the alpha particle by it's a looped A shape. Sorry, I'm not sure why it didn't show up on the actual PowerPoint here, but an alpha particle has a mass of 4, which is made up of 2 protons and 2 neutrons, and therefore it has an atomic number of 2. So if you were to look at the periodic table at what has an atomic number of 2, this is helium, thus why it is the same as a helium nucleus. So we can symbolize it by either the alpha symbol, which I just drew, or He for helium. Because it has 2 protons, it has a charge of 2+, because neutrons are neutral, so the charge is only coming from the protons. And the release of alpha particles is what is called alpha decay. So it doesn't have any electrons. This is just dealing with the nucleus, which is made up of protons and neutrons, thus the +2 charge. So in the example in your notes, there is a typo. It should say radium-226 releases an alpha particle, becoming radon-222. Radon has 2 less protons than radium, so it should say 86, not 88. So radium-226 is correct. It has a mass of 226, an atomic number of 88. It undergoes alpha decay, and 1 atom of radium becomes an atom of radon, which has a mass of 222 and an atomic number of 86. And then an alpha particle is released. Radon-88 does not exist. The atomic number 86 is for radium. So we can write these equations out in a couple of different ways. So one is using the alpha symbol and one is using the helium symbol. It is important to know, first I'm going to add in the arrows here, which should match your notes. And I'm also going to correct these to 86. Okay, so now everything should match. So when you're looking at these, 226, so the top number above radium, is equal to 222 plus 4. So 222 plus 4 is 226. So the total mass of this does not change. It's just split between the radon and the alpha particle. So this is the law of conservation of mass, even though the atoms are not being conserved. So be aware of this and be careful. On the bottom, we have 88, which is equal to 86 plus 2. So again, total number of protons is conserved. So the numbers on the top should add up, and the numbers on the bottom should add up. So even though our atoms have changed, the total stuff that's present hasn't. So the total mass of the system and the total protons has not changed. Also, I realized, sorry, the alpha symbol is missing there, so that's now filled in for you. So again, just to repeat, with the overall mass, which was equal to 226 initially with radium, it's going to be equal to that 222 when it decays into radon plus the mass of the helium atom, which is 4. And then same with the number of protons. Initially it was 88, which is equal to 86 plus 2. So alpha particles are slow and penetrate materials much less than other forms of radiation. So a sheet of paper will stop an alpha particle. So you can see here, it shows an alpha, a beta, and a gamma symbol. The top one is the alpha particle. You can see it's the biggest, it's the most massive. And because they're so big, heavy, and slow, they really can't travel through much. So it goes through air, no problem, but if it hits something like paper, it's done. It's going to stop. So alpha particles are not a concern because they can't make it through anything. So our skin is thicker, it can't make it through that. Our next particle is beta radiation. So a beta particle is an electron and is negatively charged. Because it is an electron, it is therefore negatively charged. Beta particles are represented by the following symbols. Sorry, again, this for some reason is missing, but it looks like a kind of italicized B. This should already be filled in your notes. Or the italicized E, which represents electrons. So the symbol is a Greek letter for beta. It has a mass of 0 because it's an electron and therefore has a tiny, tiny mass that's basically equal to 0. And a charge of -1 because it's an electron. So you can use either the beta symbol or the electron symbol. So electrons are very tiny, so beta particles are assigned a mass of 0. So they don't actually have a mass of 0, but their mass is 1/1836th that of a proton. So they're teeny tiny. Since there is only an electron, a beta particle has a charge of -1. Looking over our example at the bottom, we've got iodine 131, which undergoes beta decay, becoming xenon 131. A neutron has turned into a proton and then releases an electron in the process. The neutrons are neutral, so it has a mass of a proton and electron combined. So if a neutron breaks apart and forms a proton, that proton will stay in the nucleus and the electron gets released as a beta particle. So let's break this down into an equation here. So just like before, we have our two types of equations, one which uses the beta symbol, one that uses the electron symbol. Both of them will tell us the same thing. So iodine 131 has an atomic number of 53, so this is what tells us we have iodine. And it breaks down into xenon 131, so notice the mass has not changed, but because the neutron has changed into a proton, it's gained 1 proton, so the atomic number has changed from 53 to 54, and then the electron is released in the form of a beta particle. The same thing as before with the conservation of mass. 131 is equal to 131 plus 0 because the electron has no mass. And then for our atomic number, which is equal to our number of protons, we had 53, but one of those neutrons was changed into a proton. So it gains 1 proton, making it 54. And then because of the electron being released, we're adding -1 in terms of the charge overall. So originally we had 53 positive charges. When the decay happens, because of that gain in the proton, it becomes 54. And then because the electron is being released, there is a -1 charge as well. So this overall balances out to the initial charge. Proton number is conserved, as is the mass, due to the conservation of mass. Okay, so again, the top numbers balance out, the bottom numbers balance out. So beta decay occurs when a neutron changes into a proton and an electron. The proton stays in the nucleus because it can't leave the nucleus, and the electron is released. It takes a thin sheet of aluminum foil to stop a beta particle, or thin plastic. So it's still easy to stop, just not quite as easy as a piece of paper. But again, it doesn't take much to stop it in its place. Final type, gamma radiation. So gamma radiation is a ray of high energy, short wavelength radiation. So it's basically on the high end of the electromagnetic spectrum that you discussed in grade 8. Gamma radiation has no charge and no mass and is represented by the symbol. Looks kind of like actually let me redraw that. So kind of like a Y shape. Sorry, this should actually be slightly more curved. There we go. Again, those 2 zeros represent the no charge and no mass. Gamma radiation is the highest energy form of the electromagnetic radiation. It takes a thick block of lead or concrete to stop gamma rays, so not quite as easy to stop as the other two. Gamma decay results from energy being released from a high energy nucleus. So the asterisk or the star there represents extra energy. And because it's just energy that's being released, it has no charge or mass. So this is why it doesn't actually change the overall formula here. I'm just going to fill in these symbols because they're missing. So nickel 60, which we can see on the top there, with extra energy, when it decays, is still nickel 60, but without the extra energy. So notice that the asterisk has gone away because it's releasing the gamma radiation. Often, other kinds of radioactive decay will also release gamma radiation. So uranium-238 decays into an alpha particle and also releases gamma rays. So your notes are missing the little star here above the uranium. So please make sure you add that in. This is what represents the extra energy being present, which is needed for gamma radiation, for us to symbolize it. So uranium-238 with extra energy decays. First, we have regular old alpha decay. So you can see that the 238 on top is equal to 234 on thorium plus the helium mass of 4. And then same with on the bottom, we've got the 92 is equal to 90 plus 2. So that's just alpha decay. But then there's also gamma radiation being released at the same time, and this should say like that. So again, this part right here represents the alpha decay. So here is a summary of what you've seen thus far. Alpha, beta, and gamma radiation with their various symbols, what they're made up of, and a description of the radiation, the overall charge, and what it takes to stop that particular ray that's being emitted. Looking at the decay process and what it releases and what happens with the charge and mass and atomic number. So some files will be put onto Teams so you can get a bit more practice in, so make sure that you download these. More practice, which will be on Teams, as will this. So radiation and the radioactive decay summaries and nuclear equations for radioactive decay. Nuclear equations are written like chemical equations, but represent changes in the nucleus of the atoms. So just like before, the arrows are showing progression, but there's these additional symbols which show multiple things are involved. So instead of a rearrangement of atoms, it's representing changes in the nucleus. Chemical equations represent changes in the position of atoms, not changes in the atoms themselves. So this is kind of the difference there. The sum of the mass number does not change, and the sum of the charges in the nucleus does not change. So we still have balancing to do, but it's within the elements themselves rather than in the number of atoms present. So the example at the bottom is for alpha decay and shows how the overall mass and charges are conserved. So again, the top will add up to 226. So if I take 222 plus the helium atom, which shows me alpha radiation, that's going to add up to 226. And if I take the 86, which has decayed into, plus the alpha charge of +2 from the 2 protons, that's going to give me 88. So again, conserved overall while releasing energy. Mass number is protons and neutrons. So for the case of uranium, this is 238. The mass number of thorium plus the mass of the alpha particle is 234 plus 4. So 234 plus 4 will equal to 238. So we have consistency, and this is the law of conservation of mass. It's just in a different form. Same with conservation of charge at the bottom. We've got the 90 on thorium plus the 2 plus 2 on helium. Gives us the overall atomic number or number of protons, which is 92. Okay, and that is it for this lesson.